In this lesson, I'm going to explain how you can use pseudo-random numbers to randomize the items in an array. This algorithm shows a simple way to randomize an array. The outer I loop covers the positions in the array. For each position I, the algorithm picks a random number j between I and n. The algorithm then swaps the items in positions I and j and moves on to the next position. The algorithm considers each position in the array once, so if the array holds n items, the algorithm takes order n time. One detail we're thinking about is, how random is this algorithm? Is the chance of every item ending up in any particular position the same? For example, it would be bad if the last item had a 50% chance of ending up in the last position when the algorithm is finished. If there are n items in the array, then the chance of any particular item ending up in any particular position should be 1 over n. So what is the probability of an item ending up in position k? To end up in that position, it first must not have been placed in positions 1, 2, 3, and so on, up to position k minus 1. Let's consider the first probability. When the algorithm is picking an item for position 1, there are n possible items that it might pick. So the probability of our target item being picked is 1 over n. That means the probability of it not being picked is 1 minus 1 over n, or n minus 1 over n. Let's call that p sub minus 1. Now let's consider p sub minus 2, the probability that the item isn't picked for position 2. When the algorithm is picking an item for that position, there are only n minus 1 items left to consider. That means the chance of the item being picked is 1 over n minus 1. So the chance of it not being picked is 1 minus 1 over n minus 1, which is n minus 2 over n minus 1. Similarly, the probability p sub minus 3 that the item isn't picked for position 3 is n minus 3 over n minus 2. You can continue this argument to calculate all of the probabilities up to p sub minus k minus 1. Now that you know the probability of not being picked for any given position, what's the probability of the item not being picked for any position before position k? It's simply the product, p sub minus 1 times p sub minus 2 times p sub minus 3 and so on, up to p sub minus k minus 1. Plugging in the values we calculated gives this. But notice that this product can be simplified. The n minus 1 on the top of the first term cancels with the n minus 1 on the bottom of the second term. Similarly, the n minus 2 on the top of the second term cancels with the n minus 2 on the bottom of the third term. You can continue canceling terms until there are only two pieces remaining. The result is this simple expression, n minus k minus 1 divided by n. Now what's the probability that the item is picked for position k? It's the product of the probability of not being picked before position k times the probability of being picked at position k. The probability of not being picked by position k minus 1 we just calculated, so I'll plug that in. The probability of then being picked at position k is 1 divided by the number of items remaining at that point. At position k, there are n minus k minus 1 items left unassigned. So the probability of picking the item at this point is 1 over n minus k minus 1. Now we can cancel the numerator on the left with the denominator on the right. The result is just 1 over n. Because an arbitrary item has probability 1 over n of landing in any particular position k, the algorithm does arrange the items randomly, or at least as randomly as your pseudo-random number generator allows. So now you know how the algorithm works, that it runs in order n time, and that it distributes the items in the array randomly. In part 2 of this lesson, I'll describe a few of the things you can do with this algorithm. In part 1 of this lesson, I described an order n time algorithm for randomizing an array. In the second part of this lesson, I'll describe a couple of the things you can do by randomizing arrays. Before I start, however, let me point out that you don't need to use the algorithm multiple times to make an array more random. The reason you need to manually shuffle a deck of cards several times is that a shuffle isn't completely random. For example, two cards that are next to each other initially end up shuffled to positions that are relatively close together. You need to shuffle the deck several times to get it really randomized. It turns out that to really randomize a deck of cards, you need to shuffle it 7 times. Fewer than 7 shuffles doesn't really do the job, and more than 7 doesn't greatly increase the randomness. For more information on card shuffling, see this Wikipedia page. In contrast, when you run the array randomizing algorithm, any item could end up in any position with equal probability. So running the algorithm multiple times doesn't buy you anything, it just wastes time. So what can you do with the algorithm? Obviously, if you just need to shuffle the items in an array, you can use the algorithms to do that. Another way to think of this is that it generates random values without repetition. For example, suppose you're a teacher, you want to pick some random students to perform various chores, and you don't want to assign the same person to multiple tasks. One way to do that would be to randomize an array holding the students' names. Then, just read out the names until you've used enough of them. If another chore pops up, you can just call the next name. The algorithm is also useful if you want to pick a certain number of random items from an array. For example, suppose you're having a drawing and you want to give away 5 copies of a book. Suppose 30 people sign up for the drawing. A common approach to this problem is to randomly pick someone from the list to receive a book. Then you randomly pick another person to receive a book. You continue picking random people until you've picked all 5 and sent them books. The problem with this approach is that you might pick the same person twice. In that case, you need to discard that pick and try again. This is sort of like picking names from a hat, except after picking each name, you put that name back in the hat, so you might pick it again. Here's a way you might write this algorithm. The code initializes a count numPicked to keep track of the number of people selected. The algorithm then enters a loop that runs as long as we haven't picked 5 people. Inside the loop, the algorithm picks a random person. It then checks the picked array to see if that person has already been picked. If not, the code sets the picked array entry to true for that person and increments numPicked. When the algorithm has selected 5 people, the loop ends. This algorithm works. Usually it's fairly quick, but it may require some extra trips through the loop. If you're monumentally unlucky, you could randomly pick the same people again and again and take a very long time to finish. It's also a little bit inelegant in that sense. Here's another algorithm that's a bit simpler. First, the algorithm randomizes the array. It then simply gives books to the first 5 people in the array. Because every name in the array has an equal chance to end up in every position, everyone has an equal chance of landing in the first 5 positions and winning a book. This algorithm works, but it might do a lot of unnecessary work. For example, if 10,000 people sign up to win a book, you randomize a lot of items that you never use. Here's a version of the array randomization algorithm that only randomizes the first 5 positions. This is the same as the original algorithm, except it stops when it has filled the first 5 positions, so it saves some time. Of course, in a real program, you would probably want the value 5 to be a parameter, so you could randomize as much or as little of the array as you wanted. The last use for this algorithm that I'm going to talk about is randomizing other data structures. For example, suppose you want to randomize a 2-dimensional array instead of a normal 1-dimensional array. You could write an algorithm to do just that. You would need to worry about looping through the array and picking random elements for each position with equal probability. An easier solution is to copy the items into a 1-dimensional array, randomize it, and then copy the items back into the original array. Copying n items from one array to another is an order n operation, so the total time to randomize the 2-dimensional array is still order n. That should give you some ideas about what you can do with array randomization. You might want to try implementing the algorithm for picking k random values for an array of n items in your favorite programming language. When you're testing it, make sure it can put any item into any position. For example, run it a dozen or 2 times on an array holding 10 items, and make sure that every item eventually ends up in the first position.